Hello, this is my first video series, and on it we shall be explaining some corrections we can make to the periodic table. And you probably know what the periodic table looks like, because you've seen it in high school and middle school classrooms everywhere. But I'm just going to go over a quick overview.
So, this is a periodic table you're always seeing in school. So, you would have like the metals in this giant column right here, all the yellow. And then you would have your alkyne metals in this red row. Hydrogen is up here. And then over here, you would have your non-metals. And then your noble gases. And then all the way down here would be your rare earths. And yeah, that's pretty much it, you would think. But it turns out that this is definitely not it at all. This is a regular periodic table you see in classrooms everywhere. It has the elements lanthanum and actinium right here. I'm not sure if you can see it on the screen. And this two dots right here next to actinium represents the actinides, named after the element actinium. And lanthanum has this one dot right here, showing it's right after like cerium, praseodymium, neodymium, and the other rare earths, or lanthanides, named after lanthanum. Yet there are actually other types of periodic tables you probably haven't known about. This periodic table has the numbers 57 to 71 in place of lanthanide, which is down here on the periodic table. And also has the elements 89 to 103 down where actinium was supposed to be. And so these are all 15 of those groups, and they're replaced with that. Yet, there is one more type of periodic table. This periodic table, this one, has lawrencium on the bottom, the last elements in the series, and lutetium on the top, which is also the last element in the series. It turns out this final type of periodic table is the most accurate one, if you want to cut out this area right here. And I shall explain why it's the most accurate.
So how we organize the periodic table is that we just organize it from atomic number, how many protons the atom has. And because of that, we actually get this bonus fact about a periodic table, I guess, that elements in the column share similar traits. Let's take a look at the alkyne metals on the far left of the periodic table.
Hydrogen has one electron and one proton. And so that electron obviously fills out a hydrogen atom's first electron shell. Yet, the first electron shell of an element actually can hold two electrons, so hydrogen likes to bond with other elements to get a second electron to fill out its original shell. If we add a proton to that, we have helium. Helium, it has two protons in the nucleus, yet also two neutrons in the nucleus, which is its most stable isotope. And it has two electrons in its first shell. So it is completely inert. It doesn't interact with other elements that much because it's completely full. Yet, if we go one step further to lithium, we have two electrons in the inner shell and then one in the outer shell. Then we have a second shell here because the first shell is completely filled out with electrons. There's no more that can be added into there. Yet the second shell can hold 4 electrons. Obviously, you can have this extra electron out here. And yet, if you go one step further, we get to beryllium. Beryllium has 2 electrons in its outer shell, and it has 2 electrons in its inner shell. So it can have 2 more electrons in its outer shell if it wants to be completely inert, like a helium atom, or in this case a neon atom. And then you can just keep on adding electrons and protons until you get to oganesson, element 118. For instance, to show that elements in a column have similar properties, I have here the elements lithium, sodium, potassium, rubidium, cesium, and francium. These 6 elements, I can't really count today, these 6 elements, they all have 1 electron in the outer shell. This electron right here. They really like to explode when falling into water because the elements like to exchange this extra electron with the water molecules, break them apart into hydrogen and oxygen, and going. All of these elements share that property, except for hydrogen, because hydrogen is really weird. This is what the element of, say, sodium, this is what sodium would look like when you actually put it in water.
Describe it. You go.
These are some examples of the noble gases. Right here we have helium, neon, argon, krypton, xenon, radon, and it's not actually on here, but argon would be the last noble gas. It has a completely full shell. You can see over here, like in the last diagram, helium has 2 electrons. So its first electron shell is completely filled out. And if we go one step further, we have neon with 8, with its second shell completely filled out with 8. Argon is also completely filled. It has also 8 electrons in its outermost shell. So these elements are perfectly content with bonding. They don't like really bonding with anything. So they're just there, aloof. And that's where the name noble comes from. They're above everything else. They don't really like joining in all the fun with half of the other elements. Especially the next door neighbor is the halogens. So those are the noble gases.
And that brings us back to lithium and lawrencium. You see, lithium and lawrencium have the same outer shells as deuterium and scandium, and so they should belong in the same column. So you might be a little bit confused. So you know that lithium and lawrencium have to belong to deuterium and scandium, yet also they have to belong to the elements to the left of them in the lanthanide and actinide series. So you might ask, how do they actually fit into the periodic table if they have to fit both on the main body and off the main body? Well, you see, the rare earths, they actually are connected to the periodic table. It's just they're usually cut out, spliced, and put down at the bottom of the periodic table, because if they actually were added in, the periodic table would be a lot longer. This is what the image of it would look like.
This is a picture of a complete periodic table full of the entire elements, including the lanthanides and actinides. This is what it's supposed to look like. And sometimes they do mess it up. They accidentally put scandium and deuterium above lanthanum and actinium, even though that's not actually supposed to happen. And it's supposed to be over here above lutetium and lawrencium. So ignore this over here and actually put it over here. But anyways, this is obviously why we don't use this official periodic table. It's unnecessarily long, and we just don't normally use it because of that. We do have posters about this. This is just a regular periodic table. In a sense, we have explained how the lanthanides and actinides should have been on here. We can just expand it out to put them in. Let's see if I can do this. And I just expand it out. And then hopefully I can get it inside the frame. It's huge. So that is the entire thing right there. All of in its massive glory.
So now that you know why the lanthanides and actinides are connected to the periodic table, and how elements in the column are actually chemically similar, we can go on to the next video, which is about how new elements are created. and that we could add as many elements as we want to the periodic table.